Yes, sir. We can continue the session, sir.
Yeah, okay, ma'am.
Okay.
So, yes, okay, so we'll continue with the session, okay. So yes, the last one is still it is running. Okay, I'll stop this. Okay. So yeah. So as of now, what we have seen is we have designed a circuit for a single phase inverter, and for inverter, the control signal we have provided as square pulse. Okay. So when I provide a square pulse, the output you can able to see I'm getting as square pulse. Okay. So now what we are going to do is we are going to use or we are going to try other strategies like a modified sine and SPWM. Okay, so next we are going to try with two more strategies. So to do that, I'm not going to do a big change. Like I'm going to use the same multi-sim program, okay, multi-sim design. I'm not going to do any change in this. The thing is, we are going to vary only the input which you are providing to MOSFET gate terminal, right? So we don't need to do any change in our circuit. So we have to develop a logic or we have to change a logic only here. Okay, so we are going to change only this part. So these parts, right, I'm going to replace with and different logic which generates or which help us to generate a modified sine and SPWM signal. Okay, so first we'll start with a modified sine. Okay, so for that, as I already told you, we need two square pulse. Okay, to do that, we need two square signal. So as of now, I'll delete this part. Okay, so this region, right, I'm going to delete it. Okay, so this is not required. And this part's going to be same. Okay, so these things, right, it is going to be the same one. There won't be any change with this. Let it be like this, okay? So the input signal before we use a single square, right? So now we are going to change it. Okay, we are going to change it. So I'll just right click. I'll go to control and simulation, signal generation, signal generator. Okay, so the same thing. I need to change it as square. Okay, amplitude. Let me make it as 15. So in this, I'm not going to do any change. So for this phase value, I'm going to keep it as 0 only. Okay, for this square, I'm going to keep phase value as 0. And okay, so sorry, frequency, I need to change it as terminal. Okay, so it's so okay. So in the same way, I'm going to make a copy of it. Okay, so I'll be having two signal generators. So even this signal generator is going to generate a square waveform only, but the difference is I'm going to make this to generate with the phase shift of 90 degree. Okay, so both are going to create or generate a square pulse, square signal. Okay, the only difference is the phase shift between two signals will be of 90 degree. Okay, so this will be the only change. Apart from that, amplitude, frequency, all those parameters are going to be same. Okay, so let me just click OK, and we need to specify the frequency, right? So here, to specify the frequency, I'm going to use a single control for both signal generators. Okay, and next, what we're supposed to do is we have to add both these signals. Okay, so we need to add both a signal and if we add both the signal, what will happen is this one has an amplitude of 15, even this has an amplitude of 15, right? So at some point, okay, at some time, as we add both amplitude, it might go to 30 volt. Okay, so we need to restrict it. Okay, we have to bring back within minus 15 to plus 15. So if you see this signal generator like the square waveform, its maximum and minimum amplitude is minus 15 to plus 15, right? In the same way, the output after adding two signal, my output amplitude also should be between minus 15 to plus 15. So to do that, I'm going to use one comparison function like a filtering. Okay, let us consider that function will do filtering process. Okay, so if I go to comparison, here we have a function called in range and coerce. Okay, so use of this function is we'll be specifying input limit and output, sorry, minimum limit and maximum limit. Okay, to this function, we'll be specifying minimum and maximum limit. Okay, for example, for your understanding purpose, think that I'm specifying limit as 0 and 10. Okay, so if I give any value between 0 to 10 like 2, 6, 7, okay, like this, if I give any value, output I get it as the same value 2, 6, 7. Okay, think that I'm giving a value minus 5. Okay, that value is not within the range, right? So what this function will do is, instead of passing minus 5 as output, it will pass 0 as output. Okay, and the same way, if I give 17 as input, it is not coming within the range. So instead of passing 17 as output, it will pass 10 as output. Okay, so if the input value is not within the range, it will try to coerce within the range. Okay, so that is the functionality of this function in range and coerce. So X is my input, which is the addition of two signals. Okay, now I need to specify the upper limit and the lower limit. Okay, so upper limit, as I already told you, it is 15, and a lower limit, it is going to be minus 15. Okay, my final signal, right, it should be between minus 15 to plus 15 only. That is the reason we are doing like this. Okay, so we made a coercion. Okay, next we have to perform comparison and we have to pass a data, right? So the same logic, the remaining part, whatever we did in a previous one, right, the same thing. So here we'll be using greater than function. We'll be checking whether this value is greater than 2. So here we'll not use a condition called greater than 0. We'll be using a condition called greater than 2. Only then we'll be getting as a modified sign. Okay, so that is the reason I'm using greater than 2. If this condition satisfies, where is absolute value? Yeah, here it is. Okay, so I'll be passing my output signal as a trigger. Okay, and the same way, the bottom also. So we need to use comparison less than function. We'll check whether the reference signal is less than 2. Okay, so if this condition satisfies, we'll pass this data. Okay, so now only thing which we modified is we have passing switching signal in a different way. That's it. Okay, so the control strategies we have varied. Okay, so now if I run, just a minute, I'll run this again. So now you can able to see we'll be getting as a modified sign. Okay, so we can able to vary the frequency also. Okay, so compare with your pure square waveform. Okay, so compare with pure square waveform. If you provide this modified sine waveform to your motor, right? So the efficiency or the performance of the motor, right, it will improve. Okay, so yes, this is another control strategy, and the last and more efficient way is passing SPWM. Okay, so there is the one which provide a better performance when it comes to every control strategies. Okay, so you all know how to create an SPWM, right? Just we have to take one sine and triangle or sawtooth. We can take any one. Okay, and here a triangle or sawtooth wave will be used to decide the PWM frequency. Okay, the gap between PWM, right? So that is being decided by a triangle or a sawtooth function, and the sine signal frequency, right? That decides the frequency of output signal. Okay, that decides the frequency of an output signal. Like what I'm trying to say is, so let me go back to presentation. Yeah. So here, let us consider this is the positive cycle. Okay, let us consider we are starting here. Okay, so here you can able to see this starting from this point. My red color signal. Okay, it is starting from this point. So it is completing its first stop cycle here. Okay, and negative off cycle starts here. Okay, so this the starting and ending point, right? This one cycle frequency. Okay, this is being decided by our reference sine signal. Okay, and here within this PWM we have on and off time in positive off cycle and negative off cycle. In both we have on and off time, right? Even that is one cycle. Okay, so this frequency is being decided by either sawtooth or triangle waveform. Okay, so now we'll just see what should be the modification we have to do in this code. Okay, so very simple modification only. So here let me change this to, okay, so here I have not specified 2. Okay, it's fine. Okay, so I'll just do the changes. Okay, so here again for this we'll be using 0 only. Okay, so let me change this and I'll delete this part. As of now I'm going to delete these parts. Okay, so as I already told you, first we have to take a sine signal. Okay, we have to take a sine signal. I'll right click, I'll go to control and simulation, simulation, signal generation, and here we have a separate function for a sine itself. Okay, so I'll directly use it. So instead of using a signal generator, I'm directly going to use a sine signal function which directly generates a sine waveform. Okay, so in this, what are the parameters we need to configure is only a frequency. Okay, so the two we are going to configure with terminal. So I can directly click OK. So we are not going to configure anything else. Okay, so just I have made this function of frequency. That's using so here our requirement is I want to generate a sawtooth. Okay, I want to generate a sawtooth pulse and its amplitude Okay, sorry, it's been disconnected due to internet issue. Let me share the screen again. Okay, so may I know at which point it's disconnected? I'm not sure when it disconnected only. Can anyone tell me when it disconnected?
Sir, in the same slide only, sir, no issues. You can continue.
Okay, fine then.
Thank you, sir.
Yeah, so yes. So here, I'll just repeat this, okay? So here, we are going to use SPWM signal strategies. For that, we are comparing sine and a sawtooth signal, okay? So based on its output, we are going to pass a data. And here, we have our sine signal, right? So this is going to decide the final frequency of the signal, right? So for this signal only, we have to compare with 0. Okay, so this signal only we need to compare with a 0. So let me clean up this wire. Okay, even here. Okay, so once this condition satisfies, we have to pass this comparison output. Okay, so we have to pass the comparison output as an output voltage for our MOSFET gate terminal. Okay, so try to understand. So here we are doing a little bit more logic. Okay, so first we are comparing sine and sawtooth. Okay, so that is actually to provide a voltage for our MOSFET gate terminal. Okay, and here we are doing a comparison, right? This is completely based on a sine waveform, which decides the final output frequency, okay, which decides the final output frequency. Okay, so I'll just run and we'll see the output. We have completed the control strategies. Okay, so we have developed a logic to develop or generate SPWM signals. Okay, so we'll just run and we'll see this output. Okay, better I'll increase its frequency. So we can able to see it is generating negative and a positive obstacle like SPWM signal. So even more I can increase. Okay, I can stop and I can zoom and I can show you. Just a minute. I'll go to graph palette. Okay. So once I zoom in this, okay, I'll just take only the positive obstacle. Okay, you can able to see initially. Okay, once the positive obstacle starts, off time will be high, on time will be very less. Okay, as times goes, okay, you can able to see off time will be keep decreasing, on time will be increasing. When it reaches peak, on time will go to max. Okay, on time will go to the maximum value. Okay, so it's better I can compare with the sine waveform. Okay, like in a single waveform chart, I can display my output with the reference sine waveform. Okay, so to do that, here I'm going to insert with a build array. Okay, so for this another input, I'm going to provide the sine as I specified amplitude 1. I can't pass it directly. So what I can do is I'm going to increase its amplitude as 6. Okay, and this one I'm going to pass it to my another input of the function. Okay, so now if I run, you can able to see my output with a reference of a sine signal. Okay, so we can stop and I can show you. Okay, so this is just a reference signal which I have used for generating the control strategies. Okay, you can able to see this sine signal decides the frequency of my output signal. Okay, and the same way, possible I can show you this one also. So I'll just have to decrease the frequency, only then we can see. Yes. So this green color one, right? That is actually the reference, or I can say that is our triangle signal. Okay, like sawtooth signal. Okay. So this sawtooth signal frequency decides the duration or one cycle of my PWM signal. Okay, so here are two things you have to take in mind. Okay, so we have used two signal for generating the control signal. One is sine and another one is sawtooth. Okay, so sine signal determines the output signal frequency, and this sawtooth determines, okay, the sawtooth signal determines the frequency of this PWM. Okay, the frequency of this SPWM. Okay, so that is the reason we have used two signal to generate an SPWM, and these are all the different control strategies which we can provide for an inverter. Okay, so now we have done this with simulation, right? Whatever we have done, everything is a simulation part, correct? The same thing, okay, the same thing we'll be calling as proof of concept. Okay, so whatever we have done, right, so we'll be calling this as proof of concept. Okay, proof of concept in the sense, before we are starting any project, okay, like think that I'm the developer. Okay, so I have a customer, he has some requirement. Okay, so before he gives me the project, okay, he'll ask me to submit a proof of concept, like he need to be very assured that I can able to complete this project. Okay, for that I have to first I have to do a proof of concept, like this is the algorithm, I have to say these are the algorithms, or these are the techniques I'm going to use. If I use this technique, this is the output which I can get from this technique. Okay, so I have to submit all these reports. Okay, so this concept will be calling as proof of concept. Okay, so for every project, okay, whatever the project, before we are going to start, especially in industries. Okay, so if you get some project from a new customer or any customer, okay, so first the customer, right, he'll ask for proof of concept. Okay, like using this technique we can surely we can get this output. Okay, so we have to assure this to our customers. Okay, so these stuffs, right, we can easily do with LabVIEW, with the simulation. Okay, I'm not speaking about hardware part, I'm speaking about simulation. With simulation we can easily submit this proof of concept implementation. Okay, once if we completed this proof of concept, we can go for hardware simulation, like hardware implementation. For hardware implementation, right, we have to use some hardwares. Okay, so we'll be using some hardware, okay, like a DAG or PXI, those kind of hardwares. Okay, so using the we can able to do it. So these are the these are the product which we can help us to provide a proof of concept or a final testing. Like for development we need to have a lab view, and for hardware implementation either we need to go for a compact trio or compact trio GPIC. Okay, and this one, right, this is the output of simulation what I have shown you before. Okay, so this is the output, this is the simulation output. Okay, the same thing, okay, the same simulated circuit we have done on with the real circuit also. Okay, so this is the code. Okay, for the real circuit this is the code, and in this if you see the same logic, there is nothing new in this logic, whatever logic we used before, right, the same logic even here we kept. Okay, like here we are generating sine waveform. Okay, the sine data we are getting here. Okay, and we are comparing with sawtooth. Okay, and we are passing those signals, and this is like just on and off. Okay, based on the true and false, right? We are just passing the value, and here we are generating the trigger. And here the reason why we used multiple loop is the hardware. This hardware, right? It supports parallelism. Okay, so this hardware supports parallelism. That is the reason we have used parallel loops. So this parallelism, right, will help us to get a better deterministic output. Okay, so it will help us to achieve a better deterministic output. Like if I say I want to have on time only for 10 microsecond. Okay, so this parallelism will help us to do that. Okay, if you want to try to do the same thing with your system processor, right, that is not possible. The reason is our system processor is a general purpose processor. Okay, like the Intel, it might vary with different PCs. Okay, either we'll be having Intel or AMD, right? So those processors are general purpose processor. That processor meant to do the work in your system. Okay, its use cases to do the work at different works in a system. Okay, but when it comes to this hardware, okay, this hardware will be having its own processor. Okay, especially this is an stereo. Okay, so this hardware name is a stereo. So this stereo hardware has two processor, RT, real-time processor, and FPGA processor. Okay, so this code, right, this code is actually for FPGA only. So I hope you all know, so FPGA is nothing but millions of digital circuits. Okay, digital gates. So it is a digital circuit. Okay, when it comes to digital, we can easily perform a parallel circuit. And the process, right, compared with analog, the digital circuit, right, it can able to perform it in a faster way, more deterministic way. Okay, whatever we request, right, we can easily achieve through a digital circuit. That is the reason FPGA mostly will prefer in industrial use cases. Okay, so to get a more deterministic output, here we have segregated every logic. So we have kept everything in a multiple loops. That's it. Okay, apart from that, both logic are same. Okay, the same thing can be done in a single loop also. To achieve a more deterministic output, they have used multiple loops. Okay, so once we run this program, so this is the output which we get from it. Okay, so actually we have done this test on 2019. Okay, so this is the output which we get from our real circuit. Okay, using this hardware, we have tested the response of our circuit, and this is the response, or this is the output which we got from our circuit. Okay, so as I already told you, with LabVIEW, okay, if you performing simulation, okay, with the minimal change, you can able to implement the same on hardware also in real time also. Okay, so that is the advantage of LabVIEW. Okay, so here the thing which we have done is, what we have done is, whatever we seen, right? Okay, whatever we seen is, we used multisim for circuit. Okay, we used multisim for circuit, and we used LabVIEW for generating the control signal, right? When it comes to hardware implementation, okay, there is not a complete hardware implementation, okay, but a partial one. Okay, in a hardware implementation, what we have done is, instead of using a simulated circuit, we have developed the actual circuit. Okay, we have developed the actual circuit, but the control signals we provided from LabVIEW. Okay, just we have eliminated the multisim. Okay, so that we can able to test, or we can compare the performance, or we can compare the output of a real inverter and the simulated inverter. Okay, so that is the actual thing which we have represented over here. Okay, so yes, so here I have mentioned few of the example use cases where we can use this inverter. So the first one is a bidirectional converter. Okay, so like unit scale energy storage system. Okay, then medium to high voltage motor drive. Okay, and pumps. Okay, so here I have mentioned few things. Okay, in this, the one of the use cases which comes to our EV is, like, this can be used for converting from DC to AC for driving your motor. Okay, from the battery, if you want to power up your motor, right, this inverter can be used to convert from DC power to an AC power. Okay, so this is one of the use case which can able to help in EV. Okay, so this is about power inverter and controller. So next we are moving to electric traction motor. Okay, so till now whatever we have seen, right, okay, most of the faculties are already aware about it. Okay, so now, but now whatever we are going to see, right, this may be okay, so this may be new for many people. Okay, so now what we are going to do is we are going to simulate the motor. Okay, so simulation, it doesn't mean that we are going to simulate the physical appearance of the motor. No, so actually it's no. Okay, so we are going to simulate a motor which corresponds to its parameters. Okay, it's electrical parameters. Okay, if you want to perform a closed loop in a control system, we'll be calculating the mathematical model, right, like a mathematical model using a transfer function or a state space model. In the same way, for an EV, okay, for an EV, if you want to test your motor, we have some method to simulate to simulate our motors. Okay, so we are going to see what are the different methods available to simulate a motor and how it differs with every method. Okay, so these are the things we are going to discuss in this electric traction motor. Okay, this one, right, the whatever method we are going to see now, right, like the upcoming session, this is the very main part when it comes to EV. Okay, so we'll get into it. Okay, so when it comes to this electric motor simulation, we have two methods to do it. Okay, so the first one is, okay, so okay, fine, so we have different options to do it. Okay, so first of all we'll see what are the different motors which they use in EV. Okay, so these are the few motors I have listed, few motors they'll be using in EV, like SRM, then turn and signal motor, then induction motor. Okay, so these are the different motors which they use in EV. Okay, and for simulating the motor, we have two different options. Okay, first one is we can simulate through electrical motor toolkit. Okay, so there is one LabVIEW toolkit called electrical motor simulation toolkit. With that, we can able to simulate it. That is completely okay. That is completely LabVIEW. Okay, so we don't need to go to a multisim. Okay, so if we use the first method, right, we'll be completely doing it on LabVIEW. Okay, and the second method is multisim LabVIEW co-simulation. Yes, for this we have to use both multisim and LabVIEW to simulate a motor. Okay, so option B, like the second option, right, that is a regular one, like whatever we have seen now, right, more or less it looks the same. Okay, so I'm not going to focus much about option B. Okay, so our major focus will be on option A only, like using LabVIEW electrical motor toolkit. Okay, so we'll just get into it. Okay, so first we'll see what all the sequence will follow when we work with EV. Okay, it is not only about toolkit. I'm just going to tell you what will be the flow which will come when we develop a new electric vehicle. Okay, so the first one is choosing a proper motor. Okay, so we have to choose a proper motor because based on a different motor, the performance or the efficiency of our EV, right, it will vary. Okay, so we have to design a proper motor and we have to test in several conditions. Okay, so first one contains built-in motor model. So this toolkit, right, it has some motor models. Okay, we can make use of those models. Like it has a few motors, whatever I have mentioned before, right, all those motors can be modeled again. Okay, so it has an already existing model. With those models we can test it. Okay, and the second one, if it has a motor, there will be some control strategies, right, some control algorithms. Okay, so using this toolkit we can able to test those control algorithms also. Okay, so that is possible. So first and second stage, right? It is an simulation, PC based simulation. Okay, and the third one is simulating a motor in real time using FPGA. Okay, I'll just tell you what is the difference between first two option and the third option. Okay, in first two option, will not use any hardware. Okay, will not use any hardware, using some motor parameters will simulate the motor in a system itself, in a PC itself will simulate the motor and will see the response of the motor. Okay, but option C, like the third one, right? In third one, what we'll do is we'll be having some controller. Okay, so we'll be having some controller. This motor model, right, will simulate in that hardware. Okay, will simulate in the hardware. Now that hardware will act as motor, like the characteristics wise. Okay, the characteristics wise, the hardware will act as motor. Okay, so in industries, what usually they'll do is, if you take a motor, okay, so they need to run several tests in the motor before coming as a final product, right? They need to run a several tests, okay. And one more thing, they can't able to run those tests on a real motor also. In the initial stage itself, they can't able to run in a actual motor. So what they'll do is, first they'll run all the tests in a simulation, PC based simulation. Okay, next what they'll do is, the model which they develop in a PC, right? That model, like a motor model, they'll deploy in a hardware. Okay, they'll deploy in some controller. Okay, that controller or a hardware will have the same characteristics of a motor. Okay, that hardware, right, will be having a same characteristics of motor. So what they can, after that what they can do is, they can provide the required input to run a test, and they can see the response through the hardware instead of using a real motor. Okay, so this process they'll be calling as HIL, hardware in loop. Okay, so this process they'll be calling as HIL, hardware in loop. Okay, before implementing or running all the tests in an actual motor or a actual product, they will develop a mathematical model. Okay, they'll develop a mathematical model of a product. Okay, that mathematical model will be deployed in some controller. Okay, that mathematical model will be deployed in some controller. So once we deployed that controller, right, that has a similar characteristics of our actual product. So here the product, what I mean is a motor. Okay, so that hardware, right, it will be having the actual characteristics of a product. Okay, so after that what we can do is, we can do every test in that controller instead of doing the testing in a motor. Okay, if the test is failed, okay, if the test is not satisfied or if the test is failed, what they'll do is, they'll do a change, a very small change in a motor, like in a motor, what are the things they can able to vary, right? They'll vary, and they'll start from the beginning, like running the PC test, then running the hardware test, then they'll go for testing the actual product, then they'll develop as a product. Okay, this will be the flow which comes whenever we develop any product. Okay, it is therefore EV also. Okay, so yes, this motor simulation, right, we have different methods. Okay, different methods to develop this model. Okay, so here I have mentioned three different methods. Like the first one, you can able to see constant parameter model. Okay, and then the next one is variable parameter model, and the last one is FEA model. Okay, so these are the three methods to simulate a model. Like in a control system, we have a transfer function and state space model to simulate any component, right? In the same way, for motor simulation, these are the three methods to simulate a motor. Okay, control parameter, constant parameter, sorry, constant parameter model, variable parameter model, and FEA model. Okay, so actually each has its own advantage and disadvantage. Okay, so we'll start with each and every model. Okay, so for when we use this constant parameter model, okay, to use this constant parameter model, we don't need to know a much parameter about a motor. Okay, so just if you know some few parameters, right, that will be enough to simulate a motor, and all those values also will specify directly. Okay, so like if you take PM as a motor, okay, so for that just we need to specify its resistance value, then uh, quadrature axis current and a direct axis current. We have few parameters. Okay, so if you specify those parameters, that will be sufficient to simulate a motor, like number of poles. Okay, so that will be sufficient. Okay, like this constant parameter model, right, it requires only a very few motor specification to simulate a motor. Okay, as it requires very few parameters. Okay, for simulation it will take very minimal time. Okay, so just keep this in mind. Its advantage, okay, its advantages, it doesn't need a much data to simulate a model. Okay, it doesn't need a specification of a motor to simulate a model, as it doesn't require much information to simulate a model. It won't take much memory or much processing power. Okay, so this is an advantage, okay, for simulating a model, right? It doesn't need more resource to simulate it. Okay, and it has its disadvantage also. Its disadvantages, as we use very few parameters of a model, the functionality of an actual model and the functionality of the simulated, like the actual hardware, actual motor, and the simulated model, right, it may not match that accurately. Okay, so that is what we'll be calling as fidelity. Okay, fidelity in the sense prom is like how much accuracy it has. Okay, so when we use this model, the constant parameter model, uh, the response, the real-time response and the simulated response, right, it will not have that much accuracy. Okay, so there is the disadvantage of constant parameter model. Okay, so next we'll go to variable parameter model. In variable parameter model, right, to do this we should have a model file. Okay, so we should have a model file like RTD or ANSYS or external model file. Okay, so these are a file. Okay, just a file which contains a motor specifications. Okay, so don't think it's a big one. Okay, so these are all a different file format. Okay, file format which contains a motor spec. Okay, so RTD, ANSYS or external model, right, all these are a file which contains a motor spec. Okay, instead of specifying the motor specification directly, this function, right, like this model, right, it will take the motor spec from these files. Okay, compared to constant parameter model, in variable parameter model we'll be using more parameters. Okay, so compared to constant parameter model, in variable parameter model we'll be using more parameters to simulator motor. Okay, and again, as it has more parameters compared to constant parameter, it need more memory. Okay, compared to constant parameter, it need more memory to simulate it. Okay, and the same way, its accuracy compared with a constant parameter model, this variable parameter model accuracy with respect to real motor, right, it will gets better. Okay, so it will get better, it will gets better. Okay, and yes, the last one is FEA model. Even for FEA model, we need an RTT file. Okay, we need an RTT file. So when we use this FEA model, right, it will use every parameter of a motor to simulate a model, to simulate a motor model in LabVIEW. Okay, it will take each and every motor spec. Okay, so it will take each and every motor spec to simulate a model. Okay, as it uses every specification, it need a higher computation power. Okay, so as it gives every spec, it need a higher computation power. Okay, so that is its disadvantage. Its advantages, when we use this FEA model, uh, the response of the actual motor, right? The same we can achieve in a simulation if we use FEA model. Okay, so like both are like vice versa. This constant parameter model and FEA model, right? Both are vice versa. In FEA model, it exactly mimics the actual motor. Okay, the like it's performance, right? Like not a performance, it's analysis output, right? In a FPA model, we'll get a similar output of an actual motor, but it need a higher memory to process it. But when it comes to constant parameter, it doesn't need a higher memory, but the performance, right, it won't match with the actual one. Okay, so as per our requirement, we can choose any one of the model. Okay, as per our requirement, we can use any one of the model. And to do this constant parameter model, right, it doesn't require any file. Okay, to do a constant parameter model, it doesn't requires any file, but to do variable parameter model or FPM model, we should have RTD file for both or ANSYS or external model for variable parameter model. Okay, so this RTD file, right, you can easily download from this website like www.jmacinternational.com. Okay, so you can directly download from this website. If you want to create your own RTD file for your motor, okay, so think that you have a motor, you want to simulate in a lab view. Okay, for that motor, if you want to create an RTD file, what you can do is you can make use of this software JMac RT. Okay, so the same this software can be downloaded from this link. Okay, so if you want to download this software, right, you need to after creating an account, you need to wait for 3 to 4 days. Okay, only then you can able to download this software. Okay, so we can able to download this software. Using this software, you can develop an RTD file for your motor, like user defined motor. Okay, so this file is, you can easily get it from this website. Okay, if you want, you can, if you want to work right, you can directly get uh, available RTD file, or you can create your own RTD file. Anything is okay. Okay, so with this, you can able to do it. Okay, so among this, okay, so we have three models and three different motors. Okay, we have three different motors, right? So we are going to see a modeling of permanent magnet synchronous motor only. Okay, so we are going to see a modeling of permanent magnet synchronous motor. Okay, so this motor, right, it can be simulated in all the three methods. Okay, so it can be simulated through all the three methods: constant parameter model, FEA model, or variable parameter model. Okay, so it supports all three modeling. Okay, so we'll start with each one by one. Okay, so first we are going to start with constant parameter model. So if you use a constant parameter model, just we need to enter a few spec of a motor, that's it. Okay, so nothing more. Okay, so we'll just see how to do this. So to simulate it through constant parameter model, first we need to read the constant parameter model. With that we can able to simulate a motor. Okay, as of now, okay, as of now we are going to see only this part. Okay, like creating the model. Okay, we'll come to this part later, the bottom one. Okay, for these things, right, will come later. As of now, we are going to see how to simulate a motor. Okay, so first we are going to start with constant parameter model. Okay, we are going to start with constant parameter model. Let me come back to lab view. Yeah, so I can maximize my block diagram. So yes, so I'll just right click. Okay, I'll go to control and simulation. Here I can able to find there is one palette called electric motor simulation. Okay, so here I can able to find a function called electric motor simulation, and here I can able to find a palette for every motor like PMSM, ACIM or SRM. Okay, so these are all the palette which will be used for simulating the motor. Okay, when it comes to AC motor, it need an inverter, right? So for inverter also we have a design. Okay, so three-phase inverter model we have. Then if you want to do any measurement like motor speed and rotor position and Hall effect sensor measurement model, okay, so we'll be having these functions. Okay, and the same way converting from like a transformers, like okay, so even these things will be available. Okay, like three-phase current or voltage to direct and quadriaxial current or voltage. Okay, so those conversions will be available. Okay, so if you want, we can able to use these functions. Okay, as of now, as I already told you, I'm going to show you only the motor modeling. Okay, so first we are going to start only with a motor modeling. So we are going to start with PMSM motor. Okay, in this we are going to see with a constant parameter model. Okay, we are going to start with a constant parameter model. So let me take this one and I'm going to place it over here. For this function, okay, so for this function, we need to provide, okay, PMSM constant parameters. Okay, so that is fine. We can easily provide. So if I create a control, okay, so we'll get to know what are the parameters we need to specify, like motor parameters. We need to specify a number of poles, resistance, all those parameters. Okay, I have one motor spec. Okay, I'm going to use it. Okay, so that motor, in that motor, the number of pole is 4 and its resistance is 0.25 and direct action inductance is 0.00262 and quadriaxial action inductance is 0.00442 and its flux linkage 0.0271. Okay, so I have one motor spec. I have directly used it. Okay, so I have specified its every parameters. Okay, so now we'll see all other inputs. Okay, so the main one is completed. Okay, next you can able to see the output. Okay, so usually in a motor, okay, so the response what they'll check is they'll give an input and they'll check if it is a closed loop. Okay, if it is a closed loop, we can able to check the speed. Okay, we can able to check the speed, but this is just a motor model, so we can't check the speed of a motor. Okay, instead what we can do is we can check its torque. Okay, torque produced in it. Then if you want, we can check three-phase current. Okay, we can check the phase current, and if you want, we can check direct and quadriaxial current. Okay, so all these are possible. Okay, so we'll see everything. Okay, we'll just see everything. So for that, first I need to provide a voltage, and the very important thing, we need to provide three-phase voltage. Okay, so we need to provide a three-phase voltage, and then we need to specify, okay, or we need to provide rotor position like different degrees. Okay, so that is completely based on your speed. Okay, so the rotor positions, right, the different position that we can able to calculate only with the help of speed. So we have to specify both rotor position and speed, and dts is nothing but the time difference between the samples. Okay, so to generate all these things, okay, to get all these things, I have one function. Okay, already I have simulated a function which generates the voltage. Okay, which generates the voltage, and it generates the rotor position in degree with the help of speed. Okay, so I'll just right click. I have a function, I can directly take it, select a vi. So I don't know where I have actually kept, just let me check. Yeah, here it is. Yeah. So this is the function. Okay, if I open this, nothing will be there. Okay, so again inside this, even inside this, we are going to have the same functions. Okay, here you can able to see I used three sine waveform function. Okay, sine, this is sine waveform function, sine, again a sine waveform function. Okay, all sine waveform function, and you can able to see each has a phase difference of 120 degree. Okay, so this is 60 plus 120 is 180, and 180 plus 120 is 300. Okay, so I have three sine function which has a phase shift of 120, which represents three phase voltage. Okay, which represents three phase voltage. So that three phase voltages I'll be getting in this. Okay, and then okay, we have speed. Okay, so we'll be specifying the RPM. So we need to convert from RPM to degree. Okay, for that I have developed a logic that is based on logic is based on time difference between the sample and number of samples. Okay, so here this number of sample and DTS decides how long, okay, or I have to run the simulation for how much duration. Okay, that has been completely decided by this DT and samples only. Okay, I'll tell you how. Okay, I'll tell you how. There is not a problem. Okay, so this function will generate or will give a reference voltage input and a reference rotor position to provide an input for my model. Okay, so what I'm supposed to do is I have to specify the RPM. So RPM I specify some 1800. Okay, then number of samples I'll specify 50,000 samples. 50,000. Once I check here. Okay, fine. Okay, 50,000 samples and DT. Okay, so here DT I'm going to specify 2 microsecond. Okay, create a constant. I'm going to specify 2U. Okay, so I'll tell you how exactly these two are going to decide the duration of my simulation. Okay, so as of now I'll just enable this simple items label. This is number of samples, and this is time difference between the samples. DT is time difference between the sample. Okay, if I take an inverse of this, okay, if I take inverse of this, we'll get to know what to say, the sampling frequency. Okay, so I'll directly use a reciprocal function, and I'm going to create an indicator, and as of now I'm going to disable this block. Okay, so this one, if you run, its sampling frequency is, I don't know how much it is, 5 lakhs. Okay, so its sampling frequency is actually 5 lakhs. Okay, and number of sample is 50,000. Okay, so just try to understand, sampling frequency is 5 lakhs. Okay, number of sample is 50,000. So in this combination, okay, in this combination, if I run my simulation, it will run my simulation for 0.1 second. Okay, it will run my simulation for 0.1 second. If you not believe me, okay, I can just show you, like, very simple one. Okay, so I'll go to Express. I'm going to simulate a signal. Okay, input simulate signal. I'll just turn off this. Samples per second is nothing but sampling frequency. It is actually 5 lakhs, right? Yeah, I think so. So I'll just paste it over here, and this I'm going to make it as 50,000. I'll just click OK, and for this I'm going to create graph indicator, and if I run, you can able to see it simulated a signal for only 0.1 second. Okay, now I'll tell you what exactly this samples per second and number of samples. Okay, samples per second is nothing but we are saying the configuration. Okay, setting sample of sequence samples per second is nothing but setting a configuration, like how many samples should be there within 1 second. Okay, so samples per second, it is like setting a configuration. If we specify some value, it means that we are specifying like within 1 second, it should have these many samples. Within 1 second, it should have 5 lakh samples. Okay, the number of sample is nothing but how many samples I want to display. Okay, within 1 second it can have 5 lakh sample, but I want to display only first 50,000 samples. So if you want to display only 50,000 sample, it will take only 0.1 second, right? So instead of 50,000, if I specify 5 lakh, okay, samples per second is 5 lakh and number of sample is 5 lakh. Samples per second is nothing but how many samples should be there within 1 second. So I'm saying within 1 second it should have 5 lakh sample. So if I want to generate 5 lakh sample, obviously it need 1 second, right? So I have specified, okay, 1 second. Okay, it's coming. Okay, finally it came. So you can able to see it gave output for 1 second. Okay, so instead of 5 lakh, if I use 10 lakh, okay, so now it will be generating a sample for 2 seconds. Okay, so this number of sample and samples per second will decide a simulation timing. Okay, so even here it decides the simulation timing. Okay, so here I have specified a 2e minus 6. Okay, it indicates number of samples. Okay, it indirectly indicates number of samples it is going to have in 1 second. Okay, and this sample indicates how many samples I want to display. That's it. Okay, so these two indicates how much time my simulation will run. Based on this combination, my simulation will run for 0.1 second. Okay, so I'll just delete this as of now. We can proceed with the remaining part. Okay, so and I'll remove this one also. Okay, so based on this configuration, we'll get to know my simulation will run for I'll get a result for 0.1 second simulation. That's it. Okay, that is what indirectly means. Okay, so now we can proceed with the remaining connections. I need to pass a voltage. Okay, so voltage, we can't pass it directly. Like if I try to connect it directly, it will not connect it. The reason is I have to pass it through loops. Okay, I have to pass it through loops, which means voltage means the voltage value which varies with time, right? I have to pass each value one by one. Okay, I have to pass each value one by one. So we need to use a for loop. So I have connected a for loop. Then the same way will pass rotor position also. Okay, and then we need to pass RPM. So RPM we know 1800. So I'll just copy and I'll put it over here. It's just an RPM. Then DT. Okay, so even this I'll just make a copy and I'll put it over here and I can connect it in the bottom. Okay, so we have connected everything. So now this will give output of my of our three-phase current. And okay, so what else we are getting? Just a minute. Okay, then now we'll be getting direct and quadriaxial axis current, and finally we'll be getting our torque. So these are the outputs we'll be getting from this function. Okay, our mathematical model. Like we are providing an input, we are just going to get the output. Okay, so in this, first we are going to see. Okay, let me display everything better. Okay, so to display it, I'm going to take a waveform chart. Okay, so first let me just run this and I'll check whether we are getting a proper output. Just a minute. Okay, so we are getting it, but we can't pass this directly because as of now it is plotting with respect to samples. Okay, so we can't have or we can't pass it like this. So I need to convert it as waveform. Okay, so to do that, I'm going to use bundle function. So usually if you take a waveform, it will be having three different components. I can just show you. If we take this get waveform components, right, you can able to see there are three parameters: T naught, dt, y. T naught is the starting time of the signal, which will be calling as timestamp. Dt, time difference between the samples, and y, finally y, it will be the samples. Okay, the same format I have to reconstruct my signal. Okay, so what I'm going to do is, instead of pausing this directly, this information I'll pass it in the last one, that is y. Okay, then dt, this is the dt value. I can place it over here and I can connect, and time, this I can make it as 0 and I can pass. Okay, so t naught, this is actually t naught. Okay, t naught, dt and y. The same way we have to do for every functions. Okay, so I'll just make a copy of it. And here the thing is, we should not pause it directly. We have to transpose it. Okay, so these steps, right? Because inside itself, it will be giving an array output. Okay, so after taking out the data, all the data should arrange in rows. Okay, so each information data, right? It should be arranged in rows, but output, everything will be arranged in a column. So we should change it. So to change, I'm using this transpose function. So rows and columns will get interchanged. Okay, I can just connect it. So as I already told you, for this configuration, it will run a simulation for 0.1 second, right? We'll just check. Okay, we'll just check whether it is running for 0.1 second. Okay, we'll run. Okay, it is consuming memory. Okay, actually, as I already told you, this will be consuming some memory. I think so. Wait. Okay, wait for a few moments. Okay, so it got loaded. As already my Chrome, right, it will be consuming more memory. Actually, we got the output. But it is not loading. So I have not added transpose here. Yeah, so that is the problem. So I'll just add transpose here also. Just stop this. Okay, so I can do one thing. Okay, already I have a code. Okay, so here this is not responding. One second, I'll just open the code, which has in a single code, I'll be having a model for I'll be having a code for every model. Okay, I can just open it directly because my system, it is already consuming more memory, it can't able to process it. Okay, so where exactly it is. Okay, so just a minute, I'll just first stop lab view. And hereafter, obviously, we don't need multi-sim. Okay, so I'll just try to run this again. Okay, so before that, I need to specify the constant parameter value. So I'll just specify it over here. So its value is 4.25. 0.00262 00442 and 0.0271. Yeah, so I'll just try to run this again. I hope it should work now. Yeah, so yes, so this is actually a three-phase current. Okay, so this is a three-phase current output. Okay, and this is a direct and quadrilateral axis current, and this is actually the torque. Okay, so now we can able to see we got a plot for 0.09. It is actually more or less equal to 0.1. Okay, so instead of 5,000, sorry, 50,000, okay, I'm going to give it as 1 lakh. Okay, I'm going to give it as 1 lakh. So obviously it will increase from 0.1 to 0.2. Okay, so now you can able to see it completed its run for 0.2 second. Okay, the simulation run, right, it's been done for 0.2 second. Okay, so this is how we can able to simulate and we can run the testing. Okay, so better, we don't have much time. What I can do is I can directly show you the remaining models. Okay, so here what we're supposed to do is this is the code for, okay, so this one, right, this is the code for constant parameter. We have specified through constant. Okay, but if you see these two model, okay, so variable parameter model or FPA model, we are reading the information from file. Okay, so we are reading the informations from a file. Okay, from the file we are developing the model and we are checking the response. Okay, so we are checking the response from a file. Okay, so if you run this, we can able to compare all the three models. Okay, so here whatever the information you want to see, right, just we can enable and we can see only those models response. Okay, so now actually I'm displaying only the constant parameter model response. Okay, so if you want a variable parameter model, just I have to uncheck these values and I have to check in the variable parameter model. Okay, so that I can able to see three-phase current value of variable parameter of model. Okay, so yes, so this is like just a motor modeling. Okay, so if I want to say here, okay, so we have seen just till creating a model. And the next one is we have to see how to control electric motor using these models. Okay, so we have to see how to control a motor, like the mathematical controlling. Okay, so for that I have a code. Okay, I can just directly show you. Not this one. Yeah. So yes, in this it is a pure closed loop. Okay, so here we'll be having a controller, we'll be having an inverter, everything is available over here. Uh, we'll start from the constants. Okay, so here actually it is constant parameter model. So we are specifying all those informations here. Okay, motor informations, right? We have specified over here, and in this we are using three PI controllers. Okay, we are using three PI controllers. For PI controllers we need to specify the coefficients, right? All those coefficients it's been specified here. Okay, so the coefficients are specified here, and then these are all the parameters which is required for inverters. Okay, so DC input will be providing, right, all those information, then carrier frequency and carrier amplitude, those informations we have specified. And this is just an inverter parameter and mechanical parameter for an motors. Okay, so all these are a few parameters which is being required for every components. Okay, then once you come here, okay, so this is actually the modeling function. Okay, PMSM constant parameter model. This function will simulate a motor model. Okay, so this function will simulate a motor a model, and it outputs three-phase current, direct and quadrilateral axial current, and torque. Okay, so here this one, right, it might looks little clumsy because it is everything is a closed loop. Okay, so the wire will be looks like a cycled one. Okay, so it might give you a little confusion. I'll try to explain you this. Okay, I'll just try to give some space for every between every functions. Yeah, so this would be fine. Okay, so this is the first one. Okay, we have a motor. Okay, for the motor, later we'll get to know from where we are getting this input, all those stuffs. Okay, so we'll get to that later. We'll leave the input part. Okay, so as of now we'll leave the input. Okay, because all the inputs are like a feedback one. Okay, so as of now we'll leave that. Okay, from the motor, okay, we'll be getting three-phase current and a torque, right? So this three-phase current, okay, so this three-phase current you can able to see this is actually a memory. Okay, so this is actually a memory. The three-phase current, it is going back. Okay, so just a minute. Okay, so this three-phase current, it's actually going back. Just look into this wire. Okay, it is going back and it is coming to our controller. Okay, so inside this, actually we have our control system algorithms. Okay, if I open this, we're able to see we'll be having our control system blocks like our summation, all those stuffs, right? It will be inside this. Okay, so then, okay, so here everything will be controlled. So here we'll be specifying we are controlling our speed, and based on the current and position. Okay, based on, for this the feedback will be current and position. Okay, like quadriaxial current, we'll be getting a three-phase current, I think so. Yeah, we'll be getting a three-phase current, and with the help of position and number of poles, we are calculating quadriaxial current and direct axial current. Okay, and that will be controlled over here. Okay, the quadriaxial current and direct axis current, right, that is controlled over here with the help of all this parameter. Okay, by controlling or by specifying the speed. Okay, speed is the main set point. Okay, so we are going to say this is my required speed. Okay, we'll specify this. Once we specify this, these control algorithm, right, it will tell us what should be the input voltage. Okay, once we specify. Okay, so once we specify our speed, this control algorithm, okay, so like PI controller, right, it will decide what should be my input voltage for my motor. Okay, from this function, I'll be getting voltage as input. Okay, so it is actually it will be a DC voltage. Okay, so that is going to PWM block. Okay, so this PWM block, right, it will generate PWM pulse signal. Like for an inverter, we should generate a pulse signal, right? So once we pass these parameters like amplitude, frequency, and time, okay, once we specify all these parameters, it will generate a control signal for inverter. Okay, so this is actually the whole thing. Okay, it has inverter, it has a control strategies, everything is available in this single code itself. Okay, so from this, okay, so in this what we are doing is we are specifying the set point of speed, and it will tell us what should be the speed, what should be the voltage required to run for the speed. Okay, so that will be going to PWM generator, like control signal generator. So this will generate a control signal, and inside this we'll be having an inverter. Okay, so inside this we'll be having an inverter. So for an inverter we'll be passing a DC voltage and our MOSFET gate signal. Okay, we'll be passing MOSFET gate signal and the current what we require. Okay, once we pass this, this will return a voltage input for a motor. Okay, so this inverter will give voltage input for a motor. You can able to see this is the voltage output we are connected to our motor model. Okay, so this is the voltage input which we are connected to motor model, and the same way in the bottom you can able to see, okay, we have motor speed and rotor position. Okay, so this function, right, it will help us to calculate the speed and motor position. For that we need to pass, okay, our set point. Okay, so the first one is actually our speed, right? So the output speed will again will be passing as input. The same for a rotor position also. Okay, whatever the output we are getting, right, that will be passing as input again. Here the one more input which is specify is its load. Okay, so we'll specify the load for our motor. Okay, and finally we'll be getting the output voltage and RPM which it runs actually, and this is actually three-phase current. Okay, yeah, I think so. Yes, there is an three-phase current. Okay, all those informations, right, we can get it as an output. Okay, so this is like a complete closed loop, a PMS motor with an inverter. Okay, so this is a complete closed loop PMS motor with an inverter. Okay, so I'll just run this. Okay, just a minute. It should not hang. Okay, hope. Yeah, sorry. Yeah, it's fine. So here you can able to see initially speed it will be 0. We have set its speed as 1500, right? So it started from 0. It reached till 1500. Okay, so at this point it reached only for the transaction, only for the speed change. You can able to see my motor takes more torque. Okay, my motor needs more torque. Once it reaches the set point, it actually decrease the torque. Okay, and the same way current consumption also you can able to see it is very high until it reaches its set point. Okay, once it reaches its set point, you can able to see the current also will decrease. Okay, so I'll try to decrease the motor speed. Okay, I'll resume it. Okay, so even now you can able to see my blue color wire is a set point. It immediately switched to my set speed, but the motor, right, it will slowly decrease and it will slowly settle at that point. Okay, and the same way, the torque, to decrease it, right, it need to apply some force. Okay, so for that, obviously it will consume some torque, and the current also will consume again. Okay, if I resume it, okay, if I resume it, you can able to see it will be keep running at the a speed of, okay, I have set it around 490, I think so, yes, 490.92. It is running at 490.88 rpm. Okay, the torque you can able to see it is not varying, and the current also I'm getting the constant current. Okay, so now I'm going to increase it again. Let me choose it to 2000. Okay, so I'm setting my rpm as 2000. If you run again, you can able to see the torque will be high until, like, it will be consuming, it need more torque until it reaches the set point. Okay, so once it reaches set point, our torque will be reduced. Okay, in the same way for current also. Okay, so this is PC simulation. Okay, PC closed loop simulation. Okay, in the same way, we can do a hardware simulation also. So I'll just quickly move to it. So just we have seen this one. Okay, and control algorithm. When it comes to hardware simulation, we'll be using, okay, so we'll be using this hardware. This hardware name is actually PXI. Okay, so this hardware name is PXI. So this PXI, right, will act as a motor. Okay, so this PXI hardware will act as a motor. Uh, in the other word, we can say it as HIL simulator, hardware in loop simulator. Okay, so now this hardware, right, it will be having a characteristics of a motor. Okay, it will be having a characteristics of a motor. So what they can do is, whatever the test they have to do, right, they'll be running every test in this hardware. So even if any problem occurs, right, they don't need to change the motor, just they'll change the modeling, again they can run every test. Okay, so actually even we have we'll be doing this HAL test for some of the applications. Okay, so like few targets which can be used for HL applications are these things like single board controller, compact trio, industrial controller. These are some of the FPGA targets. Okay, so this is not a HL hardware. These are all few FPGA targets. Among this FPGA target, this industrial controller, this is completely meant for image processing application. Okay, so we can't use this for HAL. And then USRP radio, this is completely meant for RF. Okay, radio frequency, and this RF instrument also for RF. Okay, except these three instruments, the remaining all can be used for HAL. Okay, and this one, right, this dashboard, right, this is from Tata. Okay, they have done their testing on LabVIEW only. Okay, they have completed their test on LabVIEW. Okay, so this is their setup. Like this one, right, the left side one, this is here HIL setup, which has, or which will do the functionality of a motor. Okay, which has the similar feature of motor. And the right side one, right, this is an ECU from which we'll get a control strategies for an inverter, or if there is any communication protocol like CAN protocol, right. So for control protocol, if any communication protocol it has, it will be having those stuffs in a ECU boxes. Okay, and they will be running several tests in it. Okay, so this is the setup from Tata Motors. Okay, and yes, we don't have time for ACIM, so it's fine. It even very similar as your permanent magnet signal motor only. Okay, when we use ACIM, it means these many parameters like number of poles, then starter leakage inductance, rotor leakage inductance, magnetizing inductance. Okay, so like that we have few parameters. So to develop a modeling for induction motor, we need to specify all these parameters. Okay, only then we can able to simulate it. So as I already told you, we have one more option as multi-sim and LabVIEW motor simulation, right? For that we'll be calling a multi-sim. So in that, if you go to group called electromotor, okay, so there we can able to find machines. Okay, that you can able to obtain a few other machines like brushless DC motor, DC motor. Okay, so like few DC motors we can able to simulate from through multisim. And yeah, so this I can show you. Okay, so I'll just show you one case studies. Okay, so case study. So this one, right? I think so. This is, I don't know what is this company is actually. Okay, so this company, okay, so they have to do the testing. Okay, so they have to do the testing. If they have to do the same testing in a manual way, right? They require a more time. Okay, so what they have done is instead of doing it manually, they have used LabVIEW FPGA based hardware. They use the FPGA based hardware. As they used FPGA based hardware, they have reduced the testing time by 20 times. Okay, so they have reduced their testing time by 20 times. Okay, so the tools what they used to run this test is NI LabVIEW, whichever we are using now, and PXI Flex Rio card and CRIO. So these are a few hardwares from National Instruments which they used to run the test. Okay, and that company they used this like V test strategy method. Okay, so every company will be following different test strategies. Like when we ask our company, will be following waterfall method. Okay, in the same way, their company, right? They used a V method. Okay, this is the flow which they follow. Like first requirement definition. Okay, then requirement verification. If the requirement verification is not satisfied, they'll go to again requirement definition, they'll come back to it. Okay, next, model in loop simulation. This is PC simulation. Okay, so this is PC simulation, and this is PC control algorithm, like what we have done now. Okay, whatever we have done now, right? That is the second part. Okay, and the third one is control validation and deployed controller development, which means HAL in the sense, I have said about one controller, right? Actually, they'll be having two controllers. Okay, one controller will behave as a motor, and another controller will behave as your controllers. Like for motor to control, we need some controller, right? So another hardware will act as a controller. Okay, so then they'll run a test between this hardwares. Okay, so actually they are doing the second step over here. Okay, they are doing those steps in the third one. Okay, then code generation, code verification. So these are all the process of FPGA. Okay, so these are all the process of FPGA. Then ECU development. Okay, the electron circuit unit deployment. Okay, like they'll be replacing a hardware with actual ECU. Then ECU HIL verification. Then they'll be going for motor and inverter calibration. These are all hardware part. Okay, and then ECU integration with HIL, and finally in vehicle testing. Okay, so this is the flow which they followed in their company. Okay, so this model will be calling as V model. Okay, so as I seen this before, yeah, so as they mentioned here, actually they have completed all their tests automatically on 118 hour. Okay, 118 hour. Okay, so if they want to do this run a test manually, right, they requires around 2300 hours. Okay, they reduced it to 118 hour by replacing it with NI hardwares. Okay, so this is one of the thing which they have done, I think so 3 years before. Yeah, approximately 3 years before. Okay, so yes, what are the takeaways? The first thing, they can able to verify the ECU conditions in various conditions, like the testing, right? It's been tested for different conditions, like it includes the environmental change also. Okay, And the second one is map test case. Map test case in the sense, while running a test, I think that they are detecting some failure. Okay, so if they fix the failure, it should not disturb a working one, right? So they'll be keep validating every test continuously. Okay, so that they'll be calling as map test case. Okay, so even the third point is more or less the same thing, like performance aggressive test in the sense they'll be doing the test repeatedly, even if the test satisfies initially. If they make any change, right, they'll run every test from the beginning. That is like aggressive test. So they have done the aggressive test using this hardware. And the very important thing, they have reduced their testing time 20 times less than your tradition method. Okay, so these are the things which they have done in this. Okay, and yes, with this, I'm closing my session. Actually, I have taken a little more time. It's okay. So thank you all. If you have anything to ask, you can just ask now, either using a chat or you can use an can unmute and you can ask. Okay, and this is my contact detail. In future, if you have any requirements, right, you people can feel free to ask. You can contact me through mail or mobile number.
Sir,
And if you have any,
I will share
yeah,
your contact details to all the participants, sir, for
yeah,
further
yeah,
clarification.
just a minute. Sorry. Yeah. So this is my number. Okay, so if anyone have any queries, you can ask. Else we can wind up the session.
So anybody is having any clarifications? Okay, sir. Shall we wind up the session, sir?
Yeah, okay, ma'am. Sure. Okay,
Thank you.
so thank you all for attending this session. Okay, so